Welcome back. In the first few classes of this linear algebra course, we have focused on the concept of vectors. We have seen what vectors are, their geometric foundation, their algebraic generalizations, and their basic properties. It's time now to look at the other major item that will form the backbone of this course, namely linear systems. Of course, what you see in front of you on the top right side of the screen is a linear system. But before we go into the details of what all that mess of symbols and subscripts means, we're going to start from something a little bit easier. But again, before going there, let me just emphasize the fact that linear systems together with vectors, both in their interplay and in their relationship and in their further study, will be basically the content of the rest of this course. So, let's start simple. Let's start with something that we may consider as the atom of this topic of linear systems. We'll talk about a linear equation. A linear equation simply is an equation of the form a dot x equals c. Now, this is not an equation that one of the types of equations that you're familiar with from calculus. And in fact, when I said linear equation, probably you thought of an equation of the form y equals mx plus b. Well, that's a linear function. Okay, so remember, we're doing something which is very much related, but a little bit different. In fact, a linear function is one example of a linear equation in one dimension. But what is a linear equation in general? Well, looks like that. And let's see, what is A? A is going to be a vector of constants. So those numbers A1, A2, AN are all going to be constant. Maybe sometimes they're not going to be given explicitly, especially if we're going to look at theoretical issues, but they still have to be considered as constants. X, on the other hand, is going to be a variable vector. So it has the same number of components, otherwise we can't do the dot product, but the components are actually going to be variables. So in fact, you can think of it as a variable vector, which is how most of the time I'm going to refer to it, or as a vector of variables, if you think of each of x1, x2, and xn as a single separate variable. And then, of course, the number c is going to be a constant. Okay? So, if we compute the dot product on the left hand side, then this linear equation looks like this: a1x1 plus a2x2 plus dot 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 an xn equals c. So it's a fairly simple equation in n variables. Okay, so the good thing about it is that for x we're going to have no powers, no fractions. Well, a1, a2, an can have fractions, and so can c, but the important thing is that the variables x1, x2, xn are not in the denominator, and there is no transcendental complications like sine, cosine, exponentials, and so on and so on. Again, they can be in the coefficients, in the numbers a1, a2, an, which of course we can call the coefficients, or we normally call the coefficients, but not in the x. Now, having looked at this, now we can define a linear system of k equations in n variables as a set of simultaneous equations. And this is linear algebra, lots of words. You may want to stop, rewind, and pause and just analyze exactly what all these words mean. Okay? But a linear system pretty much looks like this: a whole bunch of k equations. Each one of them is a linear equation, so each one of them has a vector of constants, a1, a2, up to ak, and each one of them has a constant on the right hand side, c1, c2, ck. Of course, x is going to be the same in all of the equations, and remember, it's a variable vector, so it consists of a bunch of individual scalar variables. If we again develop the dot products on the left hand side, what we end up with is that a mess of coefficients and variables and subscripts and so on that we saw at the beginning. But notice that by using linear algebra notation, we can simplify an object like this and make it look a little bit simpler, make it look a little bit more manageable. Now, of course, what we do with equations, and therefore what we do with systems, is we're going to look for their solutions. What does that mean? Well, of course, a vector is going to be a solution of a linear system if it satisfies each and every one of the equation. Okay, so if I consider, oh, and by the way, we're not looking for an individual value for x1 and an individual value for x2 and so on. We're looking for an ordered set of values for x1, x2, x3 up to xn, and those same values, when plugged into each and every one of those equations, have to make the equation true. So by solving a system, what we mean is that we want to find all the ordered sets, the vectors, whose values actually satisfy each of the equations in the system. If it satisfies most of them, well, that's not good enough. It has to satisfy each and every one of them. Let's look at some terminology related with linear systems. Okay, so we're going to say that a linear systems of equation is consistent if it has some solutions. Even if it has just one, that's good enough. Is said to be consistent. Notice that I put linear and of equations in brackets because from now on, since these are the only kinds of systems that we're going to see in this course, I'm going to just make things a little bit shorter and simpler, and I'm going to drop linear and of equations. So whenever I say a system, that means a linear system of equations. Okay, so for instance, a system is inconsistent if it has no solutions, and this can happen. Maybe the equations are done in such a way that any vector that satisfies one of them cannot possibly satisfy the other one, or one of the other ones. Okay, so in other words, that we don't have the condition that all of the equations be satisfied. That condition is not true. Okay. Also, two systems are said to be equivalent if they have exactly the same solutions. So in other words, if any solution of one equation is going to be a solution, any solution of one system is going to be a solution of the other system as well, and vice versa. Okay? So the idea of an equivalent system is very important because one of the key steps that we're going to use in order to solve a linear system is actually to change it to a simpler equivalent one. Okay, so what we're going to do is we're going to start from a given system, and we're going to make some changes to it so as to make it to change it into another system which is equivalent, so same solutions, but it looks simpler and simpler and simpler until we end up with a situation where the solutions are quite apparent and evident in front of our face. Now, so how we're going to do that? Well, in this particular introductory class, where we're going to start just becoming familiar with the idea of a linear system, we're going to use a very simple, very basic method that you probably have seen in high school. Okay? And it's just a beginning one, but starting from the next class, we're going to develop a much better, much more efficient method, which will also open the way to lots more applications, lots more interpretations, and lots more fun. Okay, so let's see give one example of how we can change one system to a simpler equivalent one until we get the solution.